Hey everybody, welcome to session 11 of the SOFO sessions, the Operator Fundamentals Online, our penultimate session. We've got this IR measurements and IR mode, making them and taking them apart. Okay, so in this session, what we're going to be covering is we're going to talk about IR mode. Smart operates in two basic modes. Most of what we've been doing, in fact, all of what we've been doing, we've been in the real-time mode, but we're going to talk about IR mode. We're going to be using 8.4 version of IR mode. Sometime in the near future, we will come back and do an introduction to 8.5 because we are in the process of overhauling this mode to add a bunch of functionality and multi-measurement and all sorts of really cool stuff. So we'll come back and update you at that point. In the IR mode, there's a bunch of stuff in there for predicting intelligibility and looking at RT60 and those type of acoustical parameters. We're not going to cover them in this session. We will be touching on them when we come back. I don't know if it's in weeks or a month. It will be when 8.5 is going to be coming out, and we'll put up one for that. But remember, the manual's got a ton of stuff. The user manual has got chapters 7 through 10 are all on this mode, so there's a lot of good stuff to read there, so dig in. We're going to talk about making IR measurements, which are just the time domain view of the transfer function measurement. So we'll talk about both single channel, basically the ability to record a pop or something like that, but mostly the dual channel measurement. And specifically, I want to dig into what can we do to make our measurement better. Now, one of the things to point out here is that a lot of times we're using the IR measurement and live IR to find the measurement delay. And that's something that we don't need a really low noise floor in that. All we need to do is find the peak of the arrival energy, really simple. But as soon as you start getting into acoustical studies, it then becomes kind of interesting to really increase the dynamic range of our measurement, kind of telling sheep from goats, trying to figure out what's noise and what's just late arriving reflection. So we're going to want to increase that dynamic range, and we'll really see this when we go to IR mode. And so I want to show you a bunch of stuff in there, and we'll talk about some cool synchronized sources that we can use. In general, you probably heard me say already, it really doesn't matter where we're getting our signal from. We could be using music going through the system. We could be using pink noise from your console or a pink noise generator of some sort or Smart's noise. They're all going to give us the same basic measurement. However, I'll show you the case where actually using Smart's generator and specialized noises are going to give us some increased functionality. And then we'll go into some of the dissection tools that are in there in the IR mode, stuff that will allow us to sort of take apart the impulse response measurements for their frequency content. But keep in mind, the IR measurement, the impulse response measurement, and the frequency response measurement, the frequency domain and time domain views of the same information. But the IR mode has some tools for really delving into this stuff. So we'll get into some of that, but also remember we've got that user guide out there for you. Okay, and then as I said, this was the penultimate. We're gonna end the SOFO sessions, the Smart Operator Fundamentals Online. We'll conclude with the next session. We're gonna sum this all up, and then what we're then going to do is just do application videos and things like that. So get into actually using the tool, as you've probably been able to figure out from these sessions. These sessions are more about just operating Smart as a tool. We'll talk about the operator the exam so that you can get a level 1 certificate in here. Basically, we're telling you how this thing works as a tool, but not really delving into the applications of and the decisions you're going to be making with things like that. That's more the domain of applications training and things like that. So we're going to talk about that next session as well. So sad to see it coming to an end, but we'll have had 12 one-hour sessions to make up this whole series, and I hope it's been very useful for you guys. I'm Jamie Anderson, Director of Training, Line Cook and First Shift. We got Chris Tanjoris online, Michael riding shotgun here, and Gavin online. And of course, as I've said before, support at rationalacoustics.com. That's your go-to address for asking questions, reporting problems, things like that, UFO sightings, all that. I'm sure that that Liz and Casey will love you guys reporting UFO sightings to support. But again, if you need to get in, you want to talk training, you want to talk setting up training at rationalacoustics.com. And if you want to buy stuff, sales at rationalacoustics.com. Okay, so let's talk about IR mode. Smart has two basic modes of operation. The real-time mode is what we've been using. It basically fits the workflow of just engineering a system, measuring a system in situ, making measurements, making changes, taking other measurements, this continual workflow. Whereas IR mode sort of follows much more of a post-process idea. Let's get a really good measurement and then let's dissect it. I call it acoustic consultant mode. But basically, we're going to take the time to get a really good measurement, and then we can dig into that and do all sorts of things to see what's going on, not just with the system, but what's going on in the room. Now, just some overall things that I'm not sure if we've covered, but each window, we've only been doing one window of Smart, but you can actually run multiple windows of Smart, like multiple sessions simultaneously of Smart. In a window which has tabs in it, all the tabs are in one operational mode. Either it's in IR mode or real-time mode, but you can have two windows open. One's in IR mode, one's in real-time mode. Both modes use the same measurement engines and the same tabs that you set up. So to do the measurements, we're going to be using the transfer function measurements that we put together. And one of the things we're going to notice is we're going to be taking a measurement and we'll set a delay. We'll choose a delay time for our measurement in IR mode. If we switch to real-time mode, that measurement engine has that delay that we set. So we'll use that functionality. Okay, so we're going to go on a quick tour of IR mode. I like to take you in and say, so we're jumping over here to real-time mode, which we know and love. We're looking at the two signals we're going to be using today for measurement: a microphone placed in the room and the noise coming out of the console. So to get to IR mode, there's a couple of different ways to do it. You can go under View, real-time mode, IR mode. You notice that the hotkeys for doing it is R and I. If you notice that you're typing in, you store a trace and you're typing in a name and things are going wild, oftentimes you think you're typing into the data field, but actually you've already hit enter on the data field and now you're just typing random hotkeys. If I is one of the hotkeys you hit, you end up in a mode like, where'd my data bar go? The other way you can get there is by coming down into the lower right-hand corner in the little view section of the command bar, and that's got, it says impulse right there. And of course, when I hit that button and take us to impulse response mode, that button turns to real time. That's the take me back to real time mode. I can also get there by calling up any of the preset views that we have in there. But I figure I'll start off with a measurement. This is the worst room I've ever been in, and that's a joke from class. This is not a room. In fact, what this is, I come up here and in my view here, I'll change this view to a linear view, and what that is just recorded speech. It's just a WAV file. So in its essence, what this mode does is it just runs FFTs on WAV files. If we take an impulse response measurement and store it, we store it as a WAV file, amplitude versus time. In this case, this is recording me saying, Joe took father's shoe bench out. And so we'll do some stuff really quickly to that just to give you an idea what we can do with this mode. But if the measurement, if the wave file that we have here, so you can see the name of the wave file up here, it's shoebox.wave. But if that wave file was an impulse response, we can pull all sorts of data out of it. And again, the manual walks you through a lot of the intelligibility criterion stuff that we do in there, the STI and clarity and all those wonderful things. But what I find interesting here is what we can do in this mode is not just looking at log, etc, and linear views of these, but we can do stuff like run a bunch of FFTs to create a spectrogram of this wave file. So what I'm going to do is I'm going to set this, I'm going to run a whole bunch of 2K FFTs heavily overlapped, and I'll go ahead and calculate, and I'm going to set the dynamic range here. So again, this is the same thing as in real-time mode. These little tools on the side are the dynamic range controls for the spectrogram. In this case, in real-time mode, the spectrograph measurement we have frequency on the horizontal axis and time on the vertical axis. Because this is sort of a time-based mode, what we're looking at here actually, and I'll take the top window, change them over to linear view of that file. This top window we call the nav window, and that allows us that we can focus in on parts of this file. It's giving us the entire file, and we can crop that file right over here. But what we're looking at, like I said, this was me saying Joe took father's shoebox out. Okay, so you can see on the vertical scale we've got frequency, horizontal scale we've got time, and then color represents level. And so you see Joe took father's shoebox out. There's my de-essers going after this stuff up here. You can see that but I often ask in class, what's the difference between a vowel and a consonant? A vowel is in speech is an unrestricted flow of air. It's the powerful stuff. It's I, O. It's generally the most powerful stuff in our voice, down towards the fundamentals and the formants. They last long, anywhere from 100 to 300 milliseconds in length, whereas the consonant sounds are shorter in duration, higher in frequency. They are the fricatives, the plosives, that type of stuff. The thing is, though, that for at least for Western speech, they carry a lot of the intelligibility. So here's took. There's the t, this is ook. This is o, ook, ah, oo, ah, ow. But here is the consonant sound. The thing is, as you guys are all probably pretty well aware, one of the main jobs that we do as audio engineers is to provide intelligibility. Somebody wants to walk up to a sound system and say, number 47, your order's ready, or the plane is leaving from gate number 25, better get there. Right, Chris? Okay, so here's the thing is, as we lose these consonant sounds, we lose the intelligibility. And so this is one of the things that we're kind of focused on as sound engineers, is being able to provide clean transmission, unimpeded transmission. What you'll notice is that as this energy right here starts hanging out longer and longer in the room, it starts to occlude our ability to hear those consonant sounds. You'll notice that whenever you're sitting in a really reverberant room, somebody starts talking, their speech starts to slow down so that they have time for the previous words to decay so you can hear the attack and the consonant of the next thing. You guys have all been riding in a car singing along with a song, but are you singing the right lyrics, right? Because as you lose these consonant sounds, you lose what the words are. And so those are always funny, misheard lyrics and all that. Okay, but I like starting off a lot of times with classes with this view of human speech, just because it's so important to us. But this is giving you an idea of what this mode can do. And so what I could do is I could go in and we store our wave files, we store our impulses as wave files. So I could load an impulse response that I've made previously, and I could do Great Hall, and I could look at this guy as a a log view down here. And what we're looking at here in the impulse response, we've got time zero. The record starts at time zero. We've talked about what time zero is for our measurement. It's the moment we grab our reference signal. And then we have some amount of transit time through the system. And then we have an arrival. And then we have multiple arrivals, reflections, reverberance. We can see that reverberant decay. Now, one of the cool things about this file is that we don't just have to look at the broadband energy. This is a very powerful thing to be able, over here on the right-hand side, we can run filters on this. So this time domain file, I can choose to run octave filters, and I could look at the 16K energy, or I could look at what's happening at 8K, the 8K octave, 4K octave, 2K octave, 1K, 500, 250. One of the things you start to notice, we saw this in the last session as well, as we start getting down low, the log view of it kind of makes it look like it's multiple arrivals. If I zoom in on this plot down here, right, it looks like multiple arrivals, but that's just a function of those are sort of those zero crossings that you see on the linear view. When we look at just the envelope, the ETC, it's generally easier, particularly as you go down low, to be using the ETC view, and especially when we're measuring low frequency. One of the reasons most people start getting into the IR mode is because of its ability to give us this filtering, the ability for us to focus on lower frequencies and to use larger FFTs for doing our measurements. And so this is kind of nice. And so I can go back to, there's 125, here's 63 cycles, and I'm just going to go back to the broadband measurement. And I just want to talk about the information we're getting here, and then we're going to talk about doing the measurement, and then maybe we'll dig back into the capabilities here. In the upper window, as I said, that window is our nav window. So you can see that up here, I could zoom in on a piece of the window and see just that piece of the impulse response. Or I could zoom all the way out and look at the entire impulse response here. Okay, so that what we're seeing here, this is a stored impulse response. The locked cursor automatically jumps up to the peak. It finds the peak on it. And then we have a free cursor. And so what we're looking at here in the display, I'll try and get my free cursor to lock onto one of these arrivals. There it goes. And so what we see is the first set of numbers, 60.92 milliseconds is the arrival of the direct sound relative to time zero, or about 20.9 meters. The setting for being able to see that distance and time is in options, general, and right down here you can say cursor time readout, show me milliseconds and distance. All it's doing is taking however many milliseconds, multiplying it by the speed of sound, and giving you an architectural distance. So I have checked to use meters and Celsius, so that's why it's giving me a readout in metric. So I come back down here and I'll put this guy back up here. I don't want to, yeah, I'm burning up time just figuring out, come here. There we go. And so the green number is where my free cursor is. So that's arriving at 164 milliseconds, about 56.6 meters relative to time zero, and 34 dB down. The kind of interesting one is the last set of numbers, and that is in the brackets, is the differential cursor. And what that is telling us is about the arrival difference. So it's about 103 milliseconds difference. So what we've got is about a 35 meter reflected path, and its level is about 22 dB down. Now this is one of the reasons why I always say you want to be, if you're looking at acoustical stuff, that reflection there, if we look at the linear view of this impulse response, he barely shows up. That's that guy showing up out here. So when the question we're asking is about what's going on acoustically, what's going on with reflections and reverberance, we generally want a logarithmic vertical scale. It really helps us see what's going on with the energy in the room. Okay, and so we could use this. We could use this to be able to, say, zoom in on a piece of this arrival. So that arrival right there, and I could even take it and run an FFT on that and look at the frequency content of just this arrival. So now I've zoomed into this arrival. So now we're looking at nothing's arrived. So we're right up here in the front end of the nav window. You can see the little brackets. Now we're at this arrival, and then we can see the decay. And so all we're doing is we're choosing a chunk of the signal to look at, and we're running a DFT. So it's an arbitrary length. We're not using an FFT. FFTs are set lengths. Those are the power of 2, 1K, 2K, 4K, 8K, those things. One of the things, of course, you'll notice is as I get a narrower and narrower window, my frequency resolution goes down because my frequency resolution is 1 over the time constant of the FFT. Or I can zoom out and look at the frequency content overall. Now, what's interesting is that what we're looking at here, if I smooth this guy down, this guy, like 12th octave, if you look at since that is the impulse response of this system in this room, that's what you're going to see as a magnitude trace for the frequency response, because the frequency domain view of the impulse response is the frequency response. So that's kind of interesting, and you can zoom into the frequency content of reflections and things like that. I prefer to look at things like I like the spectrogram, because the spectrogram allows us to really see the frequency content. What I'm going to do is I'm going to change the FFT settings. We're not going to spend a lot of time on this. In fact, I fear that I've already spent too much time, but I love playing with this. But it allows us to be able to look at, let's say we've got that reflection coming in. I want to know the frequency content of that reflection, and I can see that I have got the direct arrival. This reflection, though, has some high frequency energy in it, and so does the guy following just behind it. We can also see the bottom end of the system lagging out. So that's you can do some really cool stuff taking apart impulse response. If I have time at the end of this, I'll show you some other measurements. It's always interesting and fun to kind of dig into this stuff, see what's going on in the time domain, in the response in the system. But what I'm going to do here is I'm going to jump back over, and I want to talk to you about making the impulse response and what really gives us a good impulse response. So the 4 tools plus, I'm going to give you 4 basic tools for improving our transfer function measurement, our IR measurement right here. The first, of course, is, and it's the first step when we're taking a transfer function measurement is, let's set our measurement delay, right? So we want reference and measurement to be in time with each other so that we get the best correlation. Functionally, the way I look at it is, what we've done is we've taken a chunk of the wave that we've sent into the system, and then we're looking to see how long does it take for that chunk of wave to show up at my microphone position, and do multiples of that wave show up as reflections and reverberance. And so the first thing, by timing our reference to our measurement signal, gives us the best correlation there. So that's going to help with our measurement. The second thing is measuring louder or loud enough. You don't have to have it ear bleedingly loud, but having both your acoustic level and your actual signals coming into Smart at good solid levels so that you can get a good solid measurement. So that's one of the things we want to do when we set up our measurement is get our levels set. You don't want to be down near the noise floor of your input device. And when you're in a room, you probably don't want to be measuring at the air handling noise level in the room. We want to be at a good level. You kind of get to diminishing returns when you get way up there in level. Measuring at 130 dB SPL, you don't have to do it, and it's probably a bad idea. Okay, so the third thing would be averaging. So now, instead of just taking our measurement once, let's take our measurements many times. The whole point of averaging and data averaging is to reject what is not constant, or the stuff that's spurious, noise, stuff like that. So the more times I take my measurement and average together, I suppress the noise. I should mathematically get about 3 dB better signal to noise in my measurement with every doubling of amount of data that I'm averaging. The other thing that we can do is measure with a longer time constant. So we can go from shorter time constants to longer time constants. It's another way of looking at more data. The more data we got, the more we can tell signal from noise. And like I said, this becomes about telling the sheep from the goats, telling signal arrival and reflected signal arrival from just background reverberant noise. All right, so I'm going to jump off of that slide for just a second. We're going to come over here and we're going to take an impulse response measurement. So we're set up. I've got a microphone in the room. I've got some speakers. So I'm going to go ahead and got a sub actually going on. Right, so I have some noise. So the settings for my measurement are up on the right-hand side. And so you can choose the measurement that we've got configured. I'm using the Mic 1 TF from our current tab in there. If I had other measurements set up, I could switch between the measurements there. I could switch between tabs. Right now I only have one tab configured. And then we have FFT size. Now here you can see, I say a 16K FFT is 341 milliseconds long. What does that mean? Well, 16,000 samples at a 48K sample rate is 341 milliseconds worth of data. So we're going to start with the 16K FFT. And then below that, we have our averaging setting. We're going to set it to none. So when I come down here and I hit this button right there, when I hit that button, that little play button, what it's going to do is it's going to take measurement reference signals and set it. So I have no delay set in my measurement, but this is going to take one measurement, throw the data on the screen. So it's going to be pretty fast. So I'm going to go over here. I'm going to set this guy. We'll look at the log view over here. I'll turn on my noise. Now let's take a measurement. Right? So that was really quick. It came up with an arrival time. It's got me arrival time of 39.02 milliseconds. All right, so remember, the first thing I always say is set your delay. Let's get the best mathematical correlation. So let's see if that has an impact. What I'm going to do over here is in the measurement engine, there's a button that's P in a circle. That always makes me grin. I click on that, and it's going to set the peak time to the that delay time of 39.02. So that's the only change I made, but now I've timed my reference signal to my measurement signal. And so let's try this again. I'll do the exact same measurement. And what I've got over here, I kind of play around. These controls over here are for the spectrograph, but I use them when I'm demonstrating in class. They don't control anything that has to do with what we're doing. I'm just marking that level on the screen because I want to show you what happens when I set my timing right. So, right? And so just setting my timing right, I push that noise floor down. That's very effective. Now I'm starting to see some other later arrivals. This room has got some unfriendly stuff happening. And so we'll start exposing some of that. It's still got the same delay time. It's still got 39.02. But now what we see is we're starting to see more of what's going on. Now, the thing I like about this measurement, it's really robust. I can do stuff like what I'm going to do here is I'm going to take my input. I'm going to turn on the noise. But what I'm going to do is I'm going to turn down the system. So I'm just turning it way down in level. So I can barely hear it. And what I'm going to do here is I'm going to take the same measurement, right? And I'm starting to get down to the noise floor, and we can see some low frequency stuff banging around. But it still was able to find that delay time. What I want to do though is I'm gonna measure at a decent level here. So I'm gonna bring that up. I turn the system down 25 dB. So just setting our delay and measuring at a good level has already given me a better measurement. Now in both cases, I got an accurate delay time, but maybe my question's not just, hey, what time is the direct arrival? Maybe my question is, what's going on in here acoustically in the room? So the next tool we'll bring to bear is averaging. So I'll go 2, 4. You notice how the averager goes 2, 4, 8, 16. So it's going in doubling, because every time we double, we should get 3 dB more signal and noise. It's like subwoofers, right? If I have one subwoofer, I add another subwoofer, I get, that's a significant change. I get a doubling. If I add 2 more subwoofers, I get another doubling. Let's say I had 16 subwoofers and I added a 17th subwoofer. You get virtually no change. It's a logarithmic scale, so as soon as I really have to approximately double to get a significant change in output. In this case, what I'm going to do is I'm going to go to 16 averages. It's going to take us a little bit more time, but it's still going to be relatively quick. I think I didn't hit the run button. I was waiting for that to go. But you notice how we've pushed the noise floor down even farther. We started to expose the physical setup we have in the room. If I'm measuring my microphones across the room, what you're starting to see here is energy that's hitting a sidewall in this room and now running back across the room and being reflected back. So that early on in the reflections, what you're seeing the ceiling and floor, and this stuff right here corresponds with stuff that's hit the side wall, went back to that wall, and came on back, and maybe some stuff scattering off the wall behind me, and all that sort of fun. Okay, so you notice though that we got the same 39.02. It wasn't about making that initial arrival time more accurate. It's about being able to push that noise floor down. Okay, so what I'm going to do is I'll put that back. So we'll do this one more time. But the next step I'm going to do is I'm going to increase the size of the time constant. So instead of going to a 16 KFFT, what we're going to do is I'm going to jump to a 128 KFFT, which is approximately 3 seconds long. So we're going to expand our time record, and we'll see the effect of this in our measurement. So there we've got, now that we're using a much bigger time constant, again, what we've got here is we're able to drop this noise floor down even further. And so now our time constant it's about 3 seconds long. I am not expecting energy to be banging around in this room, even 2 seconds later, a second later. The reason why I used the big time constant was actually to maximize this dynamic range. I'm starting to really expose what's going on in the acoustic field here. And so I could zoom in a little bit, make it more of an apples to apples comparison on this, but I'm really starting to see stuff going on later on here, not just that initial 39.02 arrival. Okay, so that's really cool. So we could combine these. I know people that do impulse response measurements, acousticians that do this, that will do much larger time constants. The time constants we've got go all the way up to a 512 here is about 10 seconds, 11 seconds long. And run multiples of it. So it's a type of measurement where you start the measurement running, go get some coffee, and come back. But the whole idea is to maximize that dynamic range. They're trying to do acoustical studies, what's going on acoustically, and not just broadband. Again, when we're looking at it, here is 16K, here is 8K, 4K, 2K, 1K. Now, we start to get into the fun that is this room. I'm going to put the ETC view of what's going on. Oftentimes, people are looking to, I want to tighten up the sound of my subs. When you start looking at what's going on down low, we start to realize we got some late arriving stuff. That's 500 cycles. Oh, sorry, that was 1K. There's 250. There's 125. Here's 63 cycles, and we've got significant arrivals spread out. If I just looked at my subwoofers, so I'm going to turn off my main speaker, and I'm going to do the same measurement of just my sub. I've had people come in and now I'm talking at high frequency, I'm not going to be disturbing this measurement, but here's the measurement of the subwoofers arriving, and that's problematic. You've got just from the subwoofers, we've got the main system is running down to 60 cycles, so it was in the game. But with the main system out, we've got this arrival, the first arrival, which is at 48 milliseconds thereabouts. You notice that the second arrival, which is happening some 57 milliseconds later, is actually a little bit louder because the whole room is not letting go of the energy and it's acting like a big horn. And so, there's no amount of EQ that's going to make that sound good. I need an EQ filter that cuts 63 cycles 57 milliseconds later. Go make that happen. Okay, so I'm going to go back and turn on the full range. So there's my broadband guy. Okay, so those four things, those will help you with this measurement. Basically, set your delay time, measure at good signal levels, good amount of averaging, and the bigger time constants, particularly if what you're trying to tell is reverberant and reflected energy from noise floor. Just using the bigger time constants is going to help. Or when you get into measuring low frequency, the live IRs, the largest FFT you can run in a live IR is the 32K FFT. The default is an 8K FFT. That size FFT is really, I think the technical word is shitty, for measuring subs. And so one of the things that we're working on with 8.5 is to give you a better set of tools for measuring low frequency and be able to start filtering impulse responses like I just did there. That's a good helpful way. Oftentimes when I'm setting subs to main or doing timings of low frequency elements, I'm going to go to the impulse response mode and filter the frequency range that I'm interested in and just kind of get rid of the other garbage. You notice that when we have high frequency, not to call high frequency garbage, but if high frequency is in the mix, it's the peak energy is so much outshines what's happening down low, so that there's the high frequency. If I look at 63 cycles, the peak's much lower, so it doesn't show up. It doesn't show up as well with the high frequency involved in the impulse response. But we can just filter it out. It's really cool. Okay, so we have one more trick up our sleeve, and this would be a little bit of a brain bender, but it's kind of interesting for geeks, I guess. And so there's my plus. We have the ability to do the single channel recording if just as a side note, if what you're trying to expose is what's going on acoustically in a room, you got to understand, this is strange, but you have to know why you're taking a measurement. But why I'm taking a measurement is I want to be able to predict the intelligibility or look at what the tonality of the system in the room is, or any of that. You have to measure the sound system in the acoustic environment. If instead I'm just interested in what's going on in the acoustic environment, the sound system has directivity on purpose to not excite the room, at least in the higher frequencies anyways. So when taking a measurement, if you're just trying to measure what's going on acoustically in a room, you either want a speaker, an excitation source that's omnidirectional. There's some really cool stuff out there, the Dodecs and omnidirectional speakers, or you could use an acoustic excitation device like that, a balloon, and you can just record balloon pops. And then it's just a matter of, I was going to do a balloon pop for you guys, but I don't have my gain structure set up in a way. I keep overloading the microphone when I pop the balloon. If you're going to record balloon pops or console hits, in fact, when you walk into a room, one of the first things you probably do is just clap your hands to get an idea of what's going on acoustically in the room. Huh? You know, what's going on here? So the thing is that you know, if you're going to do recording a balloon pop, what you want to do is you want to get a few balloons, all try and get them about the same size, and do a couple test pops to make sure you don't clip your input when you're doing the measurement, which we did just before the session began. But what I want to show you, this is an interesting thing. At my daughter's school, we had gotten them a set of good speakers for their small theater, and it changed their world. It was fantastic, mostly because the speakers they had in there before were old beat up speakers that were sitting on the stretch wire grid, firing across overhead, not even pointing at the people. So just putting good speakers hung in the right spot, it was a whole new world for them. Registered trademark, Disney Corporation. And so the thing is that they wanted us, they have a gymnasium that they do the whole school assembly in, and they wanted to buy new speakers for that, and this was an interesting opportunity to pop a balloon. So I hit file, I'll load this impulse response, load impulse response, and I come down here, and there is their gymatorium. Everybody loves that term. Boom. Right? And so we're talking about 4 seconds in the mid band. You walk in there, I'm sure that they would have bought whatever speaker we would have told them, but it wouldn't have made a difference. So they needed to deal with acoustic treatment. They still do in that space. But here's a situation where we just wanted to measure what was going on in the room. Have some other impulses of some flutter echoes that are fun, but we've got to get on with what we're doing. So what I'm going to do is I'm going to go back to our PowerPoint, already in progress. Okay, and so the last bit up is kind of a fun piece here. All right, so losing the data window. Okay, so when we're doing an FFT or a DFT, a discrete Fourier transform, there's a function in there called a data window that you apply when you capture your wave. You have to apply this data window because, and I have in here, what's your favorite? Hamming, Parson Welsh, Tukey, Anderson Windows, Dolby Chebyshev, Flat Top, whatever. What was interesting is on early versions of Smart, we actually exposed your ability to set that data window. And really, nobody knew what they did, and it doesn't really matter. As long as you have the same window on your reference and measurement signal, there's virtually no impact to your measurement. You just need to make sure you're using one. And worst case is people go, I don't know, I'll take my measurement without a window. It is important to know about what window you have because we're trading distortions, we're dropping the noise floor, we're getting rid of problems, but we pick up some other artifacts. And so there are reasons why you use one or the other. It really doesn't apply to what we're doing with these types of measurements. And so there are a couple places in Smart where you can actually change it, but it's only in very restricted circumstances and spectrum mode. You can't muck around with it, and we've purposely moved them out of your hands so you can't play around with them. If you are interested, there are some documents on our site. If you really want to learn about data windows and FFT data windows, we have some documents in the Rational Acoustics site, the old Smart manuals and case studies. We got the mystery of data windows. We've got the FFT fundamentals, some papers there. There you can go to Wikipedia. They've got stuff. I went to Wikipedia this morning to check the spelling a couple of those data windows. And I actually saw somebody, it was being updated at the time. So I guess that's the beauty of the shifting sands of Wikipedia. Okay, so, but if you want to learn about them, there's information out there. The good thing is you don't need to know about the data windows. That's our job, to make sure that we've got one there so you're not creating problems. Okay. So the basic assumption of the DFT, a discrete Fourier transform, is that it's grabbing your signal. So mathematically, the assumption, this is kind of a paraphrase, but mathematically, the assumption is whatever signal you got there, that represents the entire signal. Or if it doesn't represent the entire signal, it is the signal, whatever chunk you got is actually an infinite repeating signal, which is not true. So when we look at what we've got up top is a waveform, that's a chunk of pink noise. And so let's say I took just a chunk of that pink noise. So I got that pink noise wave. The mathematical assumption is that the waveform that we're measuring is just an infinitely repeating copy of that. And so what it's saying is this is what it mathematically it thinks the waveform is. Even worse, any of you guys that have ever done wave editing, if you just take two random wave files and you splice them together without dealing with that transition, you're going to get a pop and noise, and that's exactly what you get mathematically, is just crap. And so the data window functions are just there to push the beginning and ends of that wave down to zero so that you have a smooth transition. And so the trade-off is you get a raised noise floor, but you get much better data and you get a much more accurate measurement and all that. Now, that basic assumption, because we're generally using just whatever's going through the system, and it is not synced or timed or set to match our FFT settings or anything like that. So we have to use those windows. However, what we can do is we can create, and this is where this is a special case thing, is we can use a source that occurs entirely within our measurement window or that is infinitely repeating. So what I have up top is the pseudo-random noise. The pseudo-random noise is in fact a repeating noise, and you can see that waveform repeats itself. And so if we choose an FFT size chunk that's exactly the same size as the repeat of the pseudo-random noise, it turns out that any random FFT sized, any of that FFT sized chunk of that synchronized noise, when it says sync noise, it's not synchronized like to start and stop when you begin and end your measurement. It's the size of the noise repeat is synchronized to be the same size as the FFT, because when we're doing transfer function measurements, we're running continuous overlap measurements. So we're not synchronizing start and stop of our noise. It's just that the size of the noise. So we only use this functionality in impulse response mode. But there's a benefit is as soon as the size of this repeat of the noise is the same size as the data window, we don't have to use that Hamming, Hanning, Parson, Welsh, Tukey, Blackman, Harris, whatever. We don't have to use those windows, and it's going to drop our noise floor of our measurement down. That's a kind of cool thing. So I'll show you how that's done. The settings, if you go into the signal generator, so I go into my signal generator, and I say, you know what I'm going to do, okay, so let's take this measurement. Let's give ourselves a reference point here. So I'm just going to turn on noise. All right, so there's our measurement that we just had. So now what I'm going to do is I'm using a 128K FFT, so a decently long FFT. So I'm going to come over here to my noise source, and I'm going to check this box right here and say, you know what? I want to use a pseudo-random noise, and I'm going to drop IR data window. As soon as I do that, you notice that the cycle length, I can't set that cycle length. That cycle length is going to be set to whatever FFT size I'm using. But with that in place, I know then that I can drop my data window. Now, what's critical here is that with this type of measurement, it's very important that you're on the same clock. The outbound and inbound signals need to be on the same clock. If you're not on the same clock, all the benefits go out the window, and you've created a problem. There's a device called the USB Pre. USB Pre was one of the first really good, it's by Sound Devices, built like a tank, awesome device. The first version of it, when they built it, they got a chip that did digital to analog converters and the analog to digital converters, a stereo pair in and out on the same chip, and then they realized, we don't like the A to D converters on this, so they got a different chip to do A to D than D to A, but they weren't on the same clock, and so people that did this type of measurement, also you hear people talking about MLS measurements, maximal length sequence, but basically the output and the input weren't on the same clock, and so doing those type of measurements with that early device caused problems. And so those of you that were around for that probably remember that. They've since solved that problem long ago. Anyway, what I've done here is I've chose pseudorandom and drop IR data window. I'll go ahead and I'll hit OK. And so now let's see if I get a benefit from that. I hope, hopefully I do. Every now and then when you do a demo, there we go. And so in that case, I was able to drop the noise floor again an extra. Generally, you're going to get 6 to 8 dB. But now the thing is, if I was doing a transfer function measurement, to be able to tell the difference between signal and noise at 70 dB down is going to have virtually no impact on my measurement. That stuff is going to be little micro squiggle in your transfer function line. It's not necessary. It's not going to have any impact. But when you're doing an impulse response measurement where we really want to maximize that dynamic range, get that last bit of decay out of that slope, that's something where that's beneficial. Now the other measurement source that you can use it's actually a really useful measurement source is a swept sine. And so with Smaart is not set up to do a swept sine for transfer function mode. That's because in transfer function mode, we're running continuously overlapped FFTs. The key here is the entire sweep needs to take place within the entire measurement time. So we have to have some synchronization here. What I have to do is I'm going to go in and I'll go to my signal generator and I'm going to say, you know what? I want to use my pink sweep, right? And so I want to make sure I get it. I think I've got the level set right, but I'll let this go. Right? And so what this is doing is sweeping from low to high, a log swept sine. And so I've checked this box right here where it says the sweep is triggered by the impulse response. So in Smaart, as soon as I hit run on my measurement, what's going to happen is that Smaart will start the data acquisition, then start the sweep. The sweep will sweep all the way through. There's going to be time allowed for reflections and reverberance, and so it has to be synchronized to our measurement. Now, the really cool thing about the swept sine, it's a much more deterministic source. It is because we're always putting in the exact same thing. The thing about random noise, complex noise, which is what we're exciting our systems with, voice and complex noise. The thing is, we're making a basic assumption here. In our measurement, our basic assumption is that, say, the 1K energy going into the system caused the 1K energy coming out of the system. So let's take noise out of the way. Let's assume that noise is not a problem, which, careful of that assumption. But in this case, let's assume noise is out of the problem. Then the thing is that we're making an assumption that the 1K energy that went into the system caused the 1K that came out, right? But that's not completely true. We've got some level of harmonic distortion, nonlinearities in the system, and in some systems, and in some systems driven very hard, that could be a significant amount of harmonic distortion. And so the thing is that the 1K that came out of the system was predominantly caused by the 1K that went into the system, but it was also caused when 500 cycles went into the system, and when 250 and when 333. So the harmonic distortion caused by the lower frequencies is also part of that output of the system. Now, with complex noise, when we're taking a measurement, then That's just going to be one of the things you'll see is where your systems have more harmonic distortion, measurement to measurement. I'm hypnotizing you. Measurement to measurement, you're going to see some flutter and wiggle in your trace, because every time you take your measurement, you have a different combination of low frequency to high frequency, and so you have different amounts of harmonic distortion. And so the way that we deal with that is just statistically, we're going to average our measurement and get the statistical response. And so that's why we average our measurement. But one of the cool side effects when you're putting in the exact same signal every single time, it's much more, as they say, deterministic. What's really going to be interesting here, well, I think we're going to see this here, is that a weird thing happens. When I put in 1K, I get out 1K. Let's say, what are we at? We're at 39 milliseconds later, right? I put in 2K, I get 2K out 39 milliseconds later. But I also got 2K out when I put in 1K. And we're sweeping from low to high. So basically, harmonic distortion is going to show up as pre-arrivals in the impulse response. Another weird thing about the impulse response to just keep in mind, I'm not sure if this is going to make complete sense to you, but this record is circular. So mathematically, the end of this time record is the beginning of the time record. So what's going to happen is if I have pre-arrivals, sometimes they'll be arriving well before, or they'll calculate out to be well before the initial arrival. They may end up at the end of the time record. Another thing, if you're ever taking a measurement and you've swapped your reference and measurement signal and you take your delay, you might find the impulse at the very end of the record instead of the very beginning. That's a good indication that you've got reference and measurement swapped in your measurement. But without further ado, let's take this measurement, let's do it with a sweep and see what we get. Boom. So one of the things we saw is you notice that the noise floor came down even a little more. And that's because that harmonic distortion in the system is part of our noise floor as well. So that raises the noise floor. And so mathematically, we're going to get virtually the same measurement, but we're going to separate out that harmonic distortion. What I'm going to do up here in the top window, in the nav window, is I'm going to take this guy, I'm going to move my time zero. I can drag this guy out so we can really see it. And so what we see is my impulse response, but I also see this, which is the harmonic distortion in the system. So we can separate it out. It's a way of doing THD plus noise. It generally, the standard for impulse response measurements is to use a SWEP sign, and for laboratory measurements, there are a lot of things that are great about a complex noise source. And I'll let you into my mode of thought is that I want to measure the system the way we're going to excite the system. I'm not trying to get an anechoic measurement of the system. I can't go to a person listening to a show and tell them just pay attention to the direct sound and ignore the room. It would be nice if we could do that. But so I need to be, in my measurements, I need to account for what's going on acoustically in the room. I need to be able to account for its impact on tonality. Same thing with harmonic distortion, its impact on tonality and transmission quality or intelligibility. And so those things, in the tonality is in the magnitude trace, timing is in the phase trace, and transmission quality is in the coherence trace. So what we have here is there's my SWEP sign, but this measurement is really nice for being able to separate out linear and nonlinear components of the arrival. Okay, so with that bomb, we jump out and we're at the end of what I wanted to present here. Everybody fall asleep or go away. Hopefully that was helpful. Did it in an hour, almost exactly in an hour, so I feel good about that. So Michael, what do we have for questions?
Oh, we have a couple of great questions. A couple people want to know, you demonstrated how using a longer time constant will lower the noise floor. So then the question is, why don't we always use the longest time constant possible? Okay, I'll try and do this short.
there's a couple reasons. Um, that you know what? This is one that we need to do for the MTW and its effect on coherence as well. And I have an experiment. I have an experiment to set it up, but this would be about 15 to 20 minutes. So I'm just going to do a quick described. I'm going to describe what I'm talking about, but more so, I think that this is one of the application videos that I just need to do. Okay, one of the reasons why we don't use a honking big FFT is it's a ton of data, right? So you got to go back to when we were doing all this. Like when Smart started out, it was running on a 486, like 33 megahertz and 66 megahertz with a full 16 megs of RAM. So there wasn't, I mean, we're talking about big chunks of data. A 16K FFT is going to return 8,000 complex, so real and imaginary points. So that's a lot of data to track. And so the first part of the answer is that when this all started off years ago in the Stone Ages, it just wasn't possible to run really large one. Now it is possible to use these big chunks of data. And so one of the reasons why we still tend to use, particularly in the high frequencies, is shorter time constants, is because it's actually not because of the magnitude trace. And that's the thing I need to show you guys. But it's not, I can get the magnitude trace by a couple different ways. And the thing is that the size of the time constant, remember how we were talking about correlation and that third of a time constant? This was back maybe session 5 when I was talking about that correlation window. The size of that time constant is going to dictate how later arriving energy impacts our data. So does it impact it more like correlated signal or uncorrelated noise? And so one of the reasons why we tend to use the shorter time constants is not for the magnitude trace, but for the coherence trace. Because one of the things I'm trying to measure, I'm not just trying to measure, am I getting enough 4K? What is the quality of the 4K energy when it gets to people, right? And so we're using shorter time constants so that the coherence is going to start saying later arriving energy, you're destructive, you're not constructive. In fact, one of the major predictors of intelligibility is early to late arriving energy. And so if I use this, let's say a 32K FFT, which is 684 millisecond time constant, and if we used, I'm just throwing numbers at you, but let's use a third of that is about 200, let's say 220 milliseconds is sort of that correlation window. So if I have energy, reflected energy that's coming back into my measurement at, let's say 180 milliseconds late, I think pretty much every sound engineer would say that's noise, right? But mathematically, it would correlate. And so we want that to show up in the coherence trace. We want the coherence to just cry foul on that energy. And so using really big time constants causes a problem with that. So that is something, though, the using the big time constant, this has all been about optimizing FFT size. When we run the spectrum measurement, the whole thing is we use a 16K FFT because that's a trade-off between frequency resolution and just responsiveness. Because when we're running a 32K, each FFT, even though we're running 24 a second, each one is 2/3 of a second. So there's a lot of overlap. There's a lot of sluggishness to the responsiveness. And people that are using a spectrum, mix engineers, and where they're looking at a signal, you want to see that those ballistics, you want to see it react. And so that's why over the past 25 years that Smart's been around, we basically settled on a 16K FFT as the default. And so I think, though, that we are always looking at those underlying assumptions. And one of the underlying assumptions was computers can't handle those really big FFTs, and that's gone now. And so we're always in development, and we're always looking at what's coming down the road. And so that is a very timely question. So I think I'm going to leave it at that. Hopefully that wasn't too much hand waving or weirdness.
No, I think we're all set.
All right. Anything else? Who invented liquid soap and why? Anybody? Nope. Okay, so we are the next session. We're going to sum this up for at least the operator fundamentals portion of the stuff that we're doing. We're going to sum this all up and bring it to a close and talk about where it goes from here and everything like that. So thank you very much for spending your time with us, and everyone stay safe. Thank you very much.